Alright, hey gang, how's it going? We're going to be talking about the Bohr model of the atom. Okay, so it's kind of one of the very first models of the atom that allowed us to establish kind of how the subatomic particles all work together to make the electrons, protons, and neutrons all kind of function together. Alright, so what I want you to do is pause the video, jot this stuff down in the appropriate spots in the notes, okay? Because we're going to be talking about it when we're looking at the diagram here in a couple slides. Alright, so pause, take a note, pause, take notes. Alright, so Bohr model of the atom here. So some people call this the planetary model, and the idea is that the proton here, this is specifically a hydrogen atom, so you just have the one proton. But so the nucleus, if you will, is sitting here in the middle, and then these blue circles that are around it here, these represent like the paths that the electrons would take. So the idea was that the electrons are orbiting around the nucleus, kind of the same way that planets orbit around the sun. Now, in actuality, electrons don't really act like that, but that's kind of it's a beneficial way to view electrons and their energy levels to kind of start. Okay, so you got electrons, and they kind of follow these blue paths. Each of these blue paths, as you go out, we number them. Okay, and these n values here are called energy levels. All right, that's actually what the n stands for, is energy levels. Okay, so this is energy level 1, 2, 3, and 4. Okay, and notice how they correspond to circles as we get farther and farther out. These circles, also notice that these circles get closer and closer to one another as you get farther outside of the circle, or away from the nucleus. Okay, their orbits, if you will, get closer and tighter together. Okay. This kind of works on the same principle as if you play a brass instrument, you'll know that the low notes are farther apart. They start as a fifth apart, and then they go to a fourth, and then a third, and then they get closer and closer as you get higher and higher. It's all about harmonics, and it's the same kind of way with electrons orbiting around the nucleus. Okay, so you got your energy levels. They're getting far apart. The last thing I want you to know here, before we move on to the next slide, is that there's this thing called quantization. Okay, this is the idea that all energy is quantized. Okay, energy is quantized, meaning that energy will always come in specific packets. Okay, and so if we have an electron here, and he wants to get up to the second energy level, we have to give him exactly enough energy to get up past that level. If we don't give him at least that much energy, he'll never make it to this second level. So if we only give him enough, even if we get him to right here, that's not enough energy. Okay, what I want you to think about is if you're trying to walk up a ladder. Okay, so here's your ladder. I'm a great artist, can you tell? So you got, oh my goodness, how do I erase things? Let's see. Eraser. Alright, so we got our ladder here. So we got our steps. Notice how I'm making them get closer and closer together as we go up, just like our sublevels. Anyway, so we got our ladder. Okay, if you're standing on the ground and you want to get up to this level here, so we'll call this n equals 1. It's the ground state. Okay, just like you're standing on the ground before you start climbing up your ladder. Okay, n equals 1 is the ground state. So if you're standing here and you're like, oh, I'd really like to get up to n equals 2, the only way you're going to be able to get up there is if you lift your foot high enough to get up there. If you only lift your foot halfway, you're not going to magically appear on the the first step, or the n equals 2. Same thing with your electrons. If we don't give him enough energy to get all the way up here, there's no way he's going to make it. Okay. Also, we can't exist at half a sublevel. So say you're at n equals 2 and you're like, I'm kind of tired, I don't think I want to make it all the way to n equals 3, but like n equals 2 is kind of boring. So I'm just going to go halfway. That doesn't happen. You can't put your foot in midair and then imagine, and then you're not able to stand on it, right? So you got to really put all the energy up there, or you're going to be stuck at that level you're at. Another term you should know is that after we're past the ground, okay, once you're up here, it's exciting. It's exciting to be off the ground, so we call it the excited state. Okay? So when you're on the ground of your stepladder, or n equals 1, or whatever is your ground state, okay, you're on the ground, so that's your ground state. As soon as you've got enough energy to get up higher than the ground state, we call that being excited. You're at an excited state. Alright, here's another Bohr model of the atom, and we're going to talk a little bit more about how these electrons move from one level to the next. Okay, so you've got, planetary model, same thing. Notice that these circles, it's not ideal. These circles should actually be getting closer together, but we'll just kind of fudge it, pretend that they do. Okay, so we've got an electron here. He's at his ground state. Notice that his ground state is actually on 3. Okay, so electrons, their ground state is not necessarily 1. It's wherever their base stat is. And we'll talk more in the next unit when we a little bit in the next unit, and then even more in the part after that about what determines where their ground state is. So anyway, so we got this electron. He's at n equals 3. What happens is that we get some sort of light that comes in. So this is supposed to represent a wavelength of light. It comes in. Okay, and it hits this electron, and this electron goes, ooh, it's exciting, and he gets enough energy, and he pops up here. And now he gets to be at n equals 4. Okay, now remember we called this the ground state. And then, now that he's up here, he's in his excited state. He's happy to be at n equals 4. Now, two things to remember about ground state versus excited state. Ground state, we call this stable, okay? Meaning he's pretty much just going to chill there. Unless we give him enough energy, he's not going to move up, and he's never going to fall past his ground state. Okay? So at the ground state, we're stable. Well, when we're at the excited state, we call this unstable. Okay? So ground state is stable. Excited, we say that's unstable, because we've got more energy, and now we've left. You could almost imagine that there's a hole here that this electron used to be occupying. That once he's been excited and moved up out of it, he's no longer occupying that hole, and so he there's like, oh, I could come back, it's real comfy down here on the ground, I don't have to worry about falling, I don't know, whatever you want to kind of imagine this saying. Okay, so the energy comes in, excites him. Now, once he's up here, okay, he's excited, yeah, and then eventually he's going to release that energy. What comes up must come down. The general idea, and this light will come back out, and he'll fall back down to n equals 3. Now, one thing that's super interesting about this is that if he's falling the same way that he came up, so he's coming from 4 to 3, this light that gets emitted from the electron is going to be the exact same frequency as the light that was absorbed. So, if it took, we could say, okay, it took green light to make him go up, okay, it'll take green light. He'll emit green light when he comes back down. If, in another case, he had started at n equals 2, and we'd give him light, if we gave him purple light to get up here, to n equals 4, when he falls back down, he could go to this step here, and he could emit green light, and then he could come back here and emit, like red light, okay? Because in Mr. McCloud's world, green and red make purple. But anyway, don't worry about it. So the important thing to know is that this light is quantized. Okay, as you move up, you come down, and the wavelength that gets emitted is the same each time. Okay, so the important thing is when you go up, you absorb energy. When you go down, you release. Alright? Alright, once again, atomic spectra, these next couple of slides of notes, I just want you to pause, take notes. We'll talk about them on the diagram here in a second. Here's another one. Alright, so here we go. So we have continuous spectrum versus line emission spectrum. So this is just like your regular old light bulb right here. You've got your filament, and it comes down, and it's emitting just regular old white light. When it goes through a prism and we see all the colors of the rainbow. And you guys have probably seen this. This is the same way that rainbows show up, you know, Roy G. Biv and all that stuff. So this means that inside this light source that gets emitted, every single color of light shines through, hits the prism, and then comes back out the other side, and we get it on this side. Now, this guy here, if we have a specific element, okay, this is an important distinction. If we have a specific element and we get it really hot and we shine it through a prism, and we can look at it, and then only specific lines come out the other side. Okay, this is called a line emission spectrum. Okay, so we get only specific lines because in that element we've got our planetary model. Yeah. So we've got our planetary model, and our electrons are going from one to the next. Okay. And when we can only excite them to these specific energy levels, and then when they come back down, they'll emit specifically those wavelengths and frequencies of light. Okay? So the cool thing is that we can use line emission spectrums to specifically identify what elements we might have, because each individual element will have its own line emission spectrum. So here's a bunch of different ones. So hydrogen gas looks like this. We've got a red one way over here, and then we've got like this light blue color, and then it gets darker blue, and then we get some purples, lavenders. Okay, sodium is a metal, but if we heat it up and get a gas, we only get lines right here. How interesting is that? And then helium, it's just, notice how it's kind of similar to the hydrogen, right? We've got this, you know, these are kind of similar, but then and these are kind of similar, but then we get a little bit different as we get higher. Okay, and then neon, look how they're way over here, all of them. Neon is very similar to helium electronically, but its line emission spectrum is very much itself. So you can almost imagine that line emission spectrums are kind of like fingerprints to people. Okay, every single element has its own line emission spectrum, so we can actually take an unknown and get it really hot, looked at its line emission spectrum, and we can say, oh, this must have been argon, you know, just by looking at, you know, a sample of argon. This is kind of one of the reasons that we know that the sun is mostly hydrogen and helium, because we can specifically look at the line emission spectrum of the light coming off the sun, and we can see that it's really hot hydrogen and hot helium, and because they match these line emission spectrum that we have here on Earth. Anyway, so there's the Bohr model of the atom. Now this checkpoint is going to be a little different. You're going to be doing and discovering kind of this idea of line emission spectrums as a lab. So in a following video, you'll find that I explain the lab you're going to be doing, and you'll be required to come up with a purpose and a procedure for that lab. And I'll walk you through exactly what I expect you to do. But that is, and so the checkpoint is partly when you're going to come up with the purpose and the procedure, and then after you complete the lab, there's going to be questions for you to answer about what you kind of found out during the lab and kind of putting things together that way. So not a standard checkpoint for this one. It's going to be a little bit different. So if you've watched this video and you've done your pre-lab and stuff and you're working ahead, then you can go ahead and move on to part 4.